This is part 4 of the voting methods section. The final method we're going to learn is the pairwise comparison method. And what it does is it compares every candidate one-on-one with every other candidate. Now, you may want to know how many comparisons you're going to have to make, and there is a formula for that. In an election with n candidates, the number of comparisons, C, that must be made is n times n minus 1 over 2. And this is exactly the combinations formula from section 11.3 when r is equal to 2. And if you'll recall, that general formula was this. Okay, and basically what this is doing is if we're taking them by pairs, what we're doing is for all the elements we have, we are taking them 2 at a time. So the number of comparisons using this formula would be n factorial over 2 factorial times n minus 2 factorial. Okay, and I'm going to simplify this. 2 factorial is just 2 times 1, so it's 2. N factorial is n times n minus 1 times n minus 2 factorial over 2 times n minus 2 factorial. And then these cancel out, and you have this formula. So I just wanted to show you that this formula isn't magic. You already knew how to do it. Okay, so how do we actually do this? We have all the voters ranked all of them, and then we have a preference table, and then we're going to put each person up against the other, and they use X and Y candidates here. If X wins, X gets 1 point. If Y wins, Y gets 1 point. If they tie, each one gets half a point. And then after we've compared all of them, whichever candidate receives the most points wins. Okay, so going to this problem again. Which mathematician wins if the conference uses the pairwise method, and how many comparisons are required? So if we're going to need to figure out how many comparisons are required, how many candidates do we have? We have 4. Okay, so that if we have 4 candidates, the number of comparisons we need is 4 times 4 minus 1 divided by 2, which is 12 divided by 2. So we're going to need to make 6 comparisons. Okay, so I'm going to set up basically 6 different little elections here. I'm going to have Pythagoras versus Hapatia. Then I'm going to have Pythagoras versus Leibniz. Pythagoras versus Newton. And then Hapatia versus Leibniz. Hapatia versus Newton. And then finally, Leibniz versus Newton. And then I'm going to keep a count over here as they get points. Okay, so right here, if I compare Pythagoras and Hapatia, Pythagoras wins here, so that's 30 points there. Well, 30 votes. Here, Hapatia beats Pythagoras, so that's 22 votes. And then Hapatia wins here too, so that's 18 votes. Hapatia wins here, so that's 10. And then she wins here again, which is 2. And I didn't quite leave myself as much space as I would have liked here. So that's a total of 30 votes for Pythagoras and 52 votes for Hapatia. So she wins. So that's 1 point for her. Okay, Pythagoras versus Leibniz. Pythagoras wins here, but like we mentioned earlier, Pythagoras comes in dead last everywhere else. So both Pythagoras is going to win 30 points here as well, and then he's going to lose to both Leibniz and Newton every other time. So 22, 18, 10, and 2, which is again 30 to 52. So Leibniz wins 1 point. And then the same values here. So 30 to 52 again. Newton wins and gets 1 point. Okay, so Pythagoras lost in every one of his comparisons. He's going to get a big 0, but I won't write that down now until, just so you can see it for sure. All right, now let's put Hapatia versus Liveness. She wins here, 30. Leibniz wins here. Leibniz wins here. Hapatia wins here. And then Leibniz wins here. So add these up, and you get 40 to 42. So Leibniz wins there. So another point. Okay, Hapatia versus Newton. She wins 30 here and 22 here. Newton wins here, that's 18. She wins 10 and he wins 2. So add that up and you get 62 to 20. So Hapatia wins another point. So right now, Hapatia has 2, Leibniz has 1, Newton has 1. Let's see what happens here. Leibniz wins 30. Leibniz wins 22. Newton wins 18. Newton wins 10. Leibniz wins 2. So that ends up 54 to 28. And Leibniz wins. So this is 0, 2, 3, and 1. Leibniz wins. Okay, now I mentioned earlier that each of these systems is flawed. We just saw that we get, just because of this one specially designed preference table, this doesn't happen all the time, nor is it particularly common, that each of the 4 gives us a different answer. Okay, now I also mentioned that there are some criteria that political scientists use to determine whether or not something is fair. These are the 4 we're going to talk about. The majority criterion. And it says if a candidate receives a majority of first place votes in an election, meaning they receive more than 50%, then that candidate should win the election. That makes a good gut sense, good fairness sense, but that's not always going to be met. The head-to-head criterion. If a candidate is favored when compared head-to-head with every other candidate, then that candidate should win the election. Makes good sense as to what a good gut sense means to be fair, but this criterion is not always met either. The monotonicity, I think I got it, monotonicity criterion. If a candidate wins an election and in a re-election or in a real election after a straw vote, and a straw vote is just sort of like a fake vote, just to kind of see where things are standing in the beginning. So if a candidate wins the straw vote or the election, and then the only changes between that first election and the second election, or the straw vote and the real vote, are in favor of the candidate, then that candidate should win. So if you win the first and then the only changes are more people support you in the second election, then you should still win. But again, this criterion is not always met. And then the final is the irrelevant alternatives criterion. And this says if a candidate wins an election and, in a recount, the only changes are that one or more of the other candidates are removed from the ballot, then the candidate should still win the election. So if you've won and then other people drop out, then you should still win.